All right, everybody. So today, our quick little video is going to go through our new topic, which is about polygons today. And we'll be learning some facts about polygons. Now, unfortunately, due to our hybrid model, we're not going to be able to do this polygon activity here. So we're going to start with today is just what is the definition of a polygon? So we're talking about a new shape in geometry today. So we have an example of one down here. This is just a generic example of a polygon, just so we have a visual. Now, what a polygon is, like I want you to imagine making one, is we put a bunch of vertices or a bunch of dots on paper, and then we're going to connect them. Now, there's some rules on how we connect them. So the first rule that we see right here is we're only allowed to connect them with straight lines. So if I started at this vertice and I connected it to that one, that's a straight line. This is a straight line there. This is a straight line. When I connect this one, that's also a straight line. I am not allowed to do something like a curve or do something squiggly or anything like that. So something like this is a non-example of a polygon, of not a polygon, I guess I should say, because not all the edges are straight. So this is an example of a no. Now another thing, just so we can be clear about, looks like I missed a dot there, but another thing that we have for the definition of a polygon is that we have to close all of the sides. So again, if I were just to put a few random dots on my paper here and I wanted to connect them as a polygon, so I know that I have to use straight lines. That works. I know I have to use straight lines there. Again, I can't do a curved line. What we also can't do is just simply leave one of those edges open. We have to connect everything. So if it had an opening, that would not classify as a polygon. So again, this is a no example. So we're just writing no's, so we know that these are non-examples. The next one, the segments can only be connected at vertices, meaning we know we have to use straight lines. So again, I'm just making 4 random dots. I have to use straight lines from here to there. I have to use a straight line from here to there. I have to use a straight line from here to there. What we're saying is I can't take a straight line and connect it to like the middle of a side or over here. I have to connect it to one of the vertices. So if I do something like this, that would not be a polygon because there's a line segment that doesn't meet at a vertice or a vertex. And then the last one is it has to be in 2D. When it starts to be a 3D image, we call that a solid. So we're only working in 2 dimensions today. So those are the definitions of what makes a polygon. So if we're ever giving you or given a picture, then you could just see if it satisfies those requirements. So like this one here is a polygon because they only have straight edges connecting the dots. There's no openings, right? Everything is closed off from the outside, and it is on flat paper. So just a definition of what is a polygon. Once we have a polygon, so I should say vertex. Once we have a polygon, the next part of it will be naming it. And I have over here what we can do to name it. The way that you name it is you just pick a vertex, and then you follow the line segments from that vertex. So let's say on this example, I started at A. If I want to name this polygon, I have to follow the line segments in order. And I could either go this way, which would then bring me to F, and then E, and then D, and then C, and then B, and then finally I'm back to where I started, and I do not need to write that again. So notice how I followed them in order, and we used all of them, and there was no repeats. So that's just one way to name it. It doesn't matter where I start. Maybe I started at D, and then I traveled this way to E, and then to F, and then to A, and then to B, and then to C, and then back to D. Again, we're just emphasizing, it doesn't matter where I start. Like I could start at C, and then go to B, and then to A, and then F, and then E, and then D. Or of course, I could name them in that nice fashion of A, B, C, D, E, and F. As long as we're only following the straight lines, we're not cutting across to a different one. So polygons are made of sides. So the sides are just the line segments we see. So one of the line segments right there is AB. We know that line segments have flat lines over them. The next side was BC. The next side here was CD. The next side here was DE. And then we have side EF. And then we have side FA. Now, what I want you to notice is the side lengths, those letters are always next to each other in our names. And maybe we have to wrap around the end, but notice how F and A are always next to each other no matter how we name it. Just like something like side BC, they're always next to each other when we name them. Now this polygon has 1, 2, 3, 4, 5, 6 vertices, so it's going to have 6 angles, right? Angle A is an angle B, angle C, angle D, angle E, and then finally angle F. So again, notice how the angles match the vertices. So we have another vocabulary word. There's types of polygons. The first type of polygon is called a convex polygon. And then the second type is called a concave polygon. And the difference between the two has to do with diagonals. So when we think about a diagonal, I just want to define that. A diagonal is a line segment from a vertex to another one, or a vertice, to another one that is not next to it. Right, like for instance, if I started here at vertex A, going to C, that's a line segment, so that's a side. That's not a diagonal. That would be considered a side. Just like AB would also be considered a side. So if I wanted to create a diagonal from A, I'd have to go to one of these other vertices that it wasn't touching. So like that one, or that one. If I start at B here, the diagonals would be connecting to all the vertices that it's not touching on either side. I'm going to keep going for a few of those. So like if I was at this one, the ones it's not touching to the left or to the right are there in green. If I place my dot like right here, the diagonals are the ones that are not to the left or to the right, but it's the ones that they're across. Now by drawing that picture, what we notice is in a convex polygon, all the diagonals that you could possibly draw, and I didn't draw them all, I drew most of them, but all the diagonals you draw are inside the polygon. Again, if I just choose, I'm going to erase some things here. Well, I'll leave it there. If I just choose any vertex, let's say this one here, whatever diagonal I draw from it, it is going to be inside the polygon. And it doesn't matter what vertex I start at. Any diagonal will be inside. In comparison, when we look at the concave polygon, see how this point here has 2 sides? I can't connect it to that one or to that one for my diagonal because they're right next to it. But if I were to connect this one to that diagonal or that vertex right there, we can see that the diagonal lies outside of the polygon. So as long as we have one of those, so at least one diagonal lies outside the polygon. All right, so this is a bunch of facts, so we just want to make sure we memorize what is a polygon, how do I name them, and then we want to be able to break them into 2 types, convex and concave. So just a little application here. If we look at this polygon, right, we can see it's polygon. Let's name it A to B to C to D, and we go back to A. So our polygon, if we just take a moment to name it, polygon A, B, C, D. If I thought about is this convex or concave, if I pick any diagonal, there's only 2 of them for each, right? Because if I'm at D, I can't go to either side, so I have to go across. If I'm at C, that's the diagonal. If I'm at B. So I can see here that no matter what diagonal I draw, this is going to be on the, or the diagonal will be on the inside, which means that it's going to be convex. Now with this one, we do have a bunch of things going on here. I want to solve this little problem here. Like for instance, we know some things, like if I just go here, do you see how this polygon is made up of 2 triangles? This triangle here, and then this green triangle over here. So if I was going to ask you, what is this little angle here? Well, we can figure that out, right? Because in this red triangle, we know that 45 degrees plus the 65 degrees plus that missing piece, I'm just going to put a question mark there for a moment, has to add up to 180. So if we're using our calculator, when we add these together, we get 110 plus that unknown angle is 180. So that little unknown part must be 70. So let's go label that 70. I'm going to get rid of the question mark. And we could do the same thing for that green triangle too, right? This angle is 87, that one's 61. So what has to be left right there, which I'm just going to call x for a moment, I know that 87 plus that 61 plus x should equal 180. So again, when I add these two together, what do we get here? So 148 plus that missing angle. So that missing angle must be 32 degrees. Right, so what we've been able to do here is not only did we start with a polygon, and we named that polygon and said it was convex just based off of what we were looking at, but this brings up a bigger idea that when we're working with polygons, polygons can be broken into triangles. And the reason we like to break polygons into triangles is because we know a lot of stuff about triangles. So for example, like this polygon here, what they want us to look at is to divide this polygon into triangles by using diagonals just from one vertex. So for the sake of simplicity, let's just choose that vertex. So do we see how 1, 2, 3, 4, so this has one side, two sides, three sides, four sides, and five sides. So this is a five-sided polygon. But if we draw these diagonals, so when I start at that vertex, I just can't connect it to one that's either directly left or right. So when I look here though, there's five sides, but I was able, by drawing diagonals, to split this up into three different triangles. Let's try that again on the next one. If we just choose a random vertex, like this one, see how we have 1, 2, 3, 4, 5, 6 vertexes, or vertices, so 1, 2, 3, 4, 5, 6 sides. But if we connect the diagonals, so again, this one, I just can't go directly left or directly right. So that diagonal, this is a diagonal, and this is a diagonal. Do you notice now how we have 4 triangles? 1, 2, 3, and 4. So in a 6-sided shape, we're able to break that into 4 triangles. And then if we do one more, like this next one has 7 sides. I know it kind of got cut off there. They're just supposed to meet there. 1, 2, 3, 4, 5. Wait, hold on. 1, 2, 3, 4, 5, 6, 7. So from there, just so we finish that image, if I choose a vertex like that one, and I start drawing their diagonals, I think I drew one too many. Sorry. Connecting their diagonals. So this vertex to that one, right there, and right there. So when I connect all the diagonals, I see that triangle, 2, 3, 4. I see 5 triangles. So in general, what we're hoping to see is that whenever we have a polygon, an n-sided polygon, and n just stands for a number. However many sides we have on a polygon can be split into n minus 2 triangles. So for example here, that number of sides was 5, so n minus 2 was equal to 3. That's how many triangles there were. In this middle image, the number of sides was 6. If I took the number of sides and subtracted 2, that's the number of triangles. And same thing over here. The number of sides was 7. So if I took that number and subtracted 2, that gives me the number of triangles. And that's just going to be true in general. So on this next page, we have some names of polygons based on their sides. So I know I already have mine filled out. You can just take a moment to pause the video and copy them. But we know that something with 3 sides is called a triangle. Something with 4 sides is called a quadrilateral. A 5-sided shape is a pentagon. If there's 6 sides, it's a hexagon, and so on and so forth. So the number of sides we always call n. And as we're saying now, the number of triangles should be n minus 2. So something with 3 sides, obviously I can only make 1 triangle there. In a 4-sided figure, the number of triangles I'd be able to make would be n minus 2, which is only 2. In a 5-sided figure, like we did over here on our notes, if there was 5 sides, we'd be able to make 3 triangles. So we should be able to see this pattern. If there's 6 sides, 6 minus 2 means that we'd make 4 triangles. In a 7-sided figure, which we call a heptagon, there'd be 5 triangles. An octagon has 6 triangles. A 9-sided shape, which is a nonagon, has 7. 10-sided shape is a decagon. 10 minus 2 is 8 triangles. I know we skipped 11, no worries about it. A dodecagon has 12 sides, so there'd be 10 triangles. And after that, if there's too many sides, we don't give them special names anymore. We just call it an n-gon, which means there's n sides on it, whatever that number would be. So whatever the number of sides is, we always take 2 away. Now the idea there is like, why do we care though? Like, why is that so important? Well, because we know for the triangle, we know that the sum of angles in a triangle is 180. So wouldn't it be nice to have rules for other things? Like, what's the sum of a 4-sided shape? Or if I draw a 5-sided shape, what's the sum of the angles there? If I draw a 6-sided shape, you see how that question would be logical to extend forward. If we know it about a triangle, well then why don't we know it about a square or a 4 quadrilateral or a pentagon? But the good thing is we do, and we base it off of that that idea that we can draw triangles. So obviously in one triangle, there's 180 degrees. Now in a quadrilateral, if I'm able to make 2 triangles, this has 180 and this has 180. So in total, there would be 360 degrees. Let's look at that pentagon. We're supposed to be able to make 3 triangles. Right? We see this one here, which has 180. This triangle has 180, and so does that one. So if I did 3 180s, that would be 540 degrees. So in general, we're seeing this pattern, which is what we are calling our interior angle sum theorem. So the sum of all the angles on the inside of a polygon, and remember n is the number of sides. For instance, how many degrees are inside this hexagon down here? Well, the number of sides is n, so the number of triangles we make is always n minus 2, and then we multiply that by 180. So the way that we'd like to see this is the 180 represents, I'm going to move it over so I can write. The 180 of this formula represents the degrees in a triangle. And then remember, n minus 2 is the number of triangles we can make in that n-gon. So for instance here, if it has 6 sides, that means we can make 4 triangles. And if it can make 4 triangles, 4, which is n minus 2, times 180, so 4 minus 180, or times 180, excuse me, would be 720. The number of triangles I can make in a 7-sided figure is 5. So each of those triangles has 180 degrees, so that'll bring us up to 900. And we can see that pattern. If I can make 6 triangles in an 8-sided figure, well, each triangle has 180 degrees, so 6 times 180 is 1080. And we just continue that pattern. I'm just going to fill out the rest here, and you can take a moment to pause or type that into your calculator if you need a little bit more time. But again, in general, we're saying the number of sides is multiplied by 180. And it doesn't matter what way we multiply, if I multiply first by 180 or second. So the way that we're going to use that theorem then is we're going to be given something like this here, and they want us to find the measure of a certain angle. So here we can see in this polygon that we're missing the angle here. So what we notice then is it has 1, 2, 3, 4, 5, 6. So in this image, the number of sides is 6. So the number of triangles, that's n minus 2, which is 6 minus 2, which is 4. So there should be a total of 4 triangles, each that have 180 degrees in them. So 4 times 180 is 720. So all of the angles on the inside are supposed to add up to 720. So we could write this little equation. This angle plus the next angle plus 96 plus the one we don't know plus 148 plus 107 should all add up to 720. So then when we isolate that question mark just by subtraction, we're going to get 96 degrees. But again, just a quick example of how do I use this formula? Well, if I know how many sides something has, I know what all the angles should add up to. So let's try that one more time over here. What is this missing angle? Well, I notice that there's 4 sides. So if there's 4 sides, I can make the number of sides, let me label that. So the number of sides here is 4. So n minus 2, which is the number of triangles, is 2. So we can make 2 triangles here. So if we had 2 triangles and each of them has 180 degrees, there should be a total of 360 on the inside. So then that means 86 plus 142 plus 80 plus the angle we don't know should equal 360. And then by subtraction, we would see that angle is 52 degrees. So again, just making sure you know the formula, 180 times n minus 2. And then being able to apply that, how many sides do I have, how many degrees should be total on the inside, and then finding your missing. With this example here, let's roll through it again. So we can see that it's 1, 2, 3, 4, 5 sides to this polygon that I've done in green here, or sorry, in pink. Now we'll notice there's 2 missing variables here. So I think we should get rid of x first, right? Do we notice that 125 and that x form that flat line? We know flat lines add up to 180. So if there was already 125 degrees spoken for, that flat little line would have 55 degrees left. So instead of x, we know that's 55 degrees. But then if we have a 5-sided figure, right, 1, 2, 3, 4, 5, the number of triangles we could make would be 3. So each triangle has 180 degrees, and 3 times 180, of course, is where we get 540. So then all the angles on the inside, the 55, the 140, the 128, the 152, and that y that we don't know should all add up to 540. So by subtraction, I believe we get y is equal to 65. So the last part of today, we just have one other definition. This is a special type of polygon. So we're just talking about polygons in general. We'd be able to classify them as concave or convex. There's one more special type of polygon, and it's called a regular polygon. So that word regular in math means that it's both equilateral, which just means all the sides are the same length, and it's equiangular, which is just a fancy word for saying all the angles are the same. So the way that we would use that, that's just a special type of polygon. So if we were told that this was a regular pentagon, what we would know then is this side is the same as that side, which is the same as that side, which is the same as that side, which is the same as that side. But we would also know that all of the angle measures are the same. That's what I'm labeling them there. So if we wanted to find the measure of each interior angle, well, we know that there's 5 sides total. So the number of triangles would be 2 less, which is 3. So each triangle has 180 degrees. So that brings us to 540 total degrees. But if all of the angles are the same and there's 5 of them, we'd have to split up that 540 degrees into 5 equal parts. So 540 divided by 5 gives us 108 degrees. So we would know that every angle here then is 108 degrees. So that's one really nice way to find the measures of all the angles, right? We can just add them all up and divide by the total number. And that's only true if it's a regular polygon. But we also want to see another nice, easy way to find out. We want to look at one other relationship. So here, they want us to draw an exterior angle of this regular polygon. So exterior means on the outside. So we'll just extend one of the lines there. One of the line segments for a side. And they want us to find the measure of that exterior angle. Well, don't we see that that little angle completes the flat circle? So if a flat line, if the flat line is 180 and I already have 108 spoken for, that must mean there's only 72 degrees left. So our last example for today, we want to find the measures of an interior angle and one exterior angle of a regular octagon. So we see that word octagon. So we can go reference and say octagon has 8 sides. We can see that in our table there. So if I draw an 8-sided figure, and do your best at drawing these, it's okay if they're not perfect. 1, 2, 3, 4, whoops, 4, 5, 6, 7, 8. So again, that's a pretty good octagon. 1, 2, 3, 4, whoops, kind of messed it up a little bit. Let me draw a better one. It's an octagon there. So here's 1 vertice, 2, 3, 4, 5, 6, 7, and 8. So they want us to find out what are the measures of all of those angles there. But since it's a regular octagon, that's why I'm able to label them as all the same. So if there's 8 total sides, the number of triangles is 2 less. So each triangle, all 6 of them have 180 degrees. So in total, there should be 1,080. So if they're all the same, all 8 of those angles are the same, we're just going to divide all the total sum, 1080, divided by 8. So each of those angles is 135 degrees. So that's the measure of the interior angle. And then the question is also asking us to find the measure of an exterior angle. So here we just have to extend one of the sides. Doesn't really matter which one. I'm just going to choose this one down here. And they want us to find the measure of that angle. But again, I hope we see that the green angle inside the polygon was 135 degrees. And then that little purple part just completes the flat line. So there's 180 total in that flat line. The green part was 135. So if I took away 135 from 180, I would get 45 degrees. So each exterior angle will be 45 degrees. Like if I drew this one here, this would also be 45 degrees because of the same argument. If I drew that exterior angle, same argument there. So that's our notes for today. I'll post this completed version on the module as well. But make sure going through the video is usually a lot better than just reading completed notes. So have a good day.